Hi, and welcome to Dr. Vanderveen's AP Chemistry podcast. Tonight we're talking about reaction kinetics and rate laws. We have several objectives for this podcast. There are things you need to be able to do because this is an extremely important topic in AP Chemistry. So what you need to be able to do is you need to be able to write and interpret rate expressions. You need to be able to analyze kinetics data to determine reaction order. You need to be able to write rate laws and calculate the rate constant. And you need to be able to use graphical analysis to determine reaction order. So there's a lot of different things we need to do. None of them are particularly hard, but they're very, very important. I'd like to start by talking about reaction rates. When chemists talk about reaction rates, they're talking about how fast the reaction is going. And this can be measured by looking at some property that changes in the reaction that you can relate back to moles of reactants, or products for that matter. And you want to see how that changes with time, because this is a rate. How fast the reaction is going depends on several things. It can depend on the concentration of the reactants. It can depend on the temperature of the reaction, whether or not a catalyst is present. It also depends on the nature of the reactants. For example, are they liquids versus solids? That's going to affect your reaction rate because it all really comes down to collisions. So there's a lot of different things that can affect the rate. Now, one thing we like to be able to write are rate expressions. Right? And so when we say that a rate is a change in some property over a change in time, we're choosing some property that can be measured that relates back to the moles. So common properties that are chosen might be absorbance, molarity. If you've got a gas phase reaction, you might do gas pressure. So there are a lot of different choices that you have in terms of the property to measure. Now, if you've got the balanced equation, you can write a rate expression from the balanced equation, right? Because assuming that all of your reactants and products don't have the same coefficients, that is going to affect the rate at which they disappear or appear. In general, we have this generic reaction. We can say that for products, the rate is going to be positive. We're going to put a positive sign, whereas for reactants, it's negative. All right? And the reason we're doing this is because the reactants are disappearing while the products are appearing. We want to get the same rate overall for the reaction regardless of what we measure, and so the sign convention gives us rates that are always positive. All right? The reaction rate that you measure is always positive. All right, and then what you do is you do 1 over the coefficient times the change in property over the change in time, and that's generally true. What this allows us to do is, as I mentioned, to get the same value for the rate regardless of whether you're monitoring the disappearance of a reactant or the appearance of the product. You want to get the same thing. But I do want to point out that if your coefficients are different, the actual substances may appear and disappear at different rates. But when you talk about the overall rate of the reaction, we're sort of converting it all back to the same answer for that reaction under those particular set of conditions. Now, in general, reaction rates get slower with time. You have fewer and fewer collisions. Your concentration is getting lower. You can see for both the red and blue lines, the slopes get shallower and shallower as you go on. So reaction rates typically get slower. All right. Chemists often like to talk about instantaneous rates, where you take the slope of a tangent line. You can see that these two lines have very different slopes. In this region, it's quite a bit steeper than in the blue region, and this is because the reaction is slowing down. You have fewer and fewer molecules that can collide with each other, and that's going to slow you down. All right. So the instantaneous rate is the preferred way to find the reaction rate. In particular, chemists like to use the initial rates. And that's the instantaneous rate right at the beginning, when the data is almost linear. And that's considered to be the most reliable measure of the rate of the reaction. And that's what you would be comparing when you're doing your studies. You want to try and compare them under a similar conditions each time. So usually it's the initial rates that people are looking at. Right? Exactly how the rate depends on the concentration, though. I mean, we've been talking about these generalities that, oh, it slows down. You know, we can talk about instantaneous rates. But exactly how the rate depends on the concentration is a more complicated issue. We can figure it out, but we have to do other experiments. Right? And the only way you can figure out this information is to do experimentation. You cannot get it from the balanced equation, and that's a very important point. It's a very common mistake that I don't want you to make. All right? So if you've got a reaction, we're going to stick with a really simple reaction, and we're just going to focus on the reactants. I don't really care right now what the products are. We're just going to focus on the reactants. So if we have a reaction where A plus B combine to form products, and we're saying that the coefficients here are 1, but that's actually not something we need to know right now. We can write a general rate law for this. We can say that the rate is equal to some constant times the concentration of A raised to a power n times the concentration of B raised to a power m. Now these exponents, or these powers, are called the order of the reaction. So n is the order of the reaction for A, and m is the order of the reaction for B, and k is the rate constant. It's the proportionality constant that makes it all work together. And chemists studying reactions and how they work in kinetics really are very interested in the order of the reaction, because this gives you quite a bit of information about how the reaction is proceeding. We'll actually talk about that in a separate podcast. All right, but what the reaction order shows you is the mathematical relationship between the concentration and the rate. It gives you a way of actually quantifying that. Not, oh, as the concentration gets larger, the rate increases. We're being much more specific. Right? If your exponents come out to be 1, we say it's first order. All right? This could be n or m here, by the way. I'm just being general. If your exponent comes out to be 2, we say that it is second order. Now, the order of the reaction theoretically can be almost anything. Practically speaking, the orders of reactions are usually either first order or second order. Occasionally, you will see 0 order. That is possible. Higher order reactions, though, as I understand it, are very rare. And so we're not really going to worry about them. In theory, these exponents can be fractions, negative numbers, anything. But practically speaking, they usually come out to be 0, 1, or 2, 1 or 2 being the most common. All right. Now, the sum of the exponents in the rate law gives the overall reaction order. And that will be important later when we go to work out the value of the rate constant and its units. Knowing the overall reaction order just makes that a little bit easier. All right. Now, I want to remind you, I said this before, but I don't think I can overemphasize this. The only way you can determine the reaction order for a given set of reactants in a particular reaction is to do initial rate experiments, or to do experiments that give you this information. It cannot be determined from the coefficients of the balanced equation. Don't make that mistake. So a very common way to figure out the reaction order is to do initial rate experiments. And you need multiple trials where you can do this. And so we're going to look at a data set and look at how the concentrations of the reactants change and what this does to the initial rate. And we can use this to figure out reaction orders. So here's a data set. Take a moment, pause the podcast, write this down. We're going to be working with this data, so it will be worth your while to have this written out for the 3 trials here. All right. So the first thing I want to do is compare experiments 1 and 2. Now you'll notice in experiments 1 and 2, the concentration of A is constant. I'm not changing the concentration of A, but I am changing the concentration of B. I'm changing it by a factor of 2. Now, if you look at the rate in trials 1 and 2, the initial rate of these two trials was unaffected. All right. There was no change at all. Well, if I take the rate and divide it by the change in the concentration, all right, that will actually give me the overall reaction order. Well, the rate didn't change, and so even though the concentration changed by a factor of 2, what this tells me is that this reaction is 0 order in B. As long as there's B to react, the presence of B doesn't affect the rate. Right? So it's 0 order in B. Let's go on and look at some other trials from this experiment. We have to compare 2 trials and see if we can figure out the reaction order relative to A. That's our next thing. So let's look at experiments 1 and 3. Now, if you look at experiments 1 and 3, the concentration of B is unchanged. But what I've done with the concentration of A is I've doubled it. Now, if we look at the rates, all right, I went from a rate of 4 times 10 to the minus 5th moles per second to a rate of 16 times 10 to the minus 5th moles per second. Well, that's a 4-fold change. So if I take my change in the rate and divide it by the change in the concentration, that tells me that it goes up as the square of the concentration. In other words, I can conclude that this reaction is 2nd order in B. I'm sorry, in A. I misspoke. It was 0 order in A. I said that wrong again. It's 2nd order in A, 0 order in B. That's what we got by comparing experiments 1 and 2, and then comparing experiments 1 and 3. All right, so we can write an overall rate law based on this data. We can say that the rate is equal to the rate constant times the concentration of A squared times the concentration of B raised to the 0 power, which in essence we can just ignore. All right, overall, this reaction is order. Now what we can also do, now that we have a rate law, is calculate the rate constant. To do this, we just pick any one trial. Any single experiment. And we're going to substitute our data in. All right, and solve for the rate constant. So let's see. We know that the rate is equal to the rate constant times A squared. So the rate constant, which is always written with a lowercase, usually italicized k, is equal to the rate divided by the concentration of A squared. All right, and so I'm going to pick trial 2, not that it matters, but I can pick any one. For trial 2, the rate was 4 times 10 to the minus 5th molar per second, divided by the concentration of A squared, which was 0.100 molar squared. I suppose I should go get my calculator and do this math out. All right, so I got that out, and I did all my math, and I got a value of 0.004. And if I look at my units, I had molar per second and then molar squared. All right, so one of these will cancel out. So what I end up for my units overall is per molar per second. All right, and so these are the things you really need to be able to do. I thought it might be useful for us to look at another set of data just to get a little extra practice with this. All right, so we want to find the rate law and determine the rate constant for another set. So let's look at trials 1 and 2. All right, if we look at experiments 1 and 2, I'm going to hold the NO concentration constant. I double the hydrogen concentration. And when I do that, I see that the rate increases. Well, I doubled the rate when I double the concentration, that means that this is first order in hydrogen. All right, for this rate. Then I guess I want to look at the first and third trials. It won't always be comparing the first and second and the first and third trials. It just worked out that way for this particular set of problems that I chose. If we look at the first and third trials, I'm going to hold the hydrogen concentration. I'm going to double the NO concentration. And then if I look here, turns out that the rate went up by a factor of 4. 4.92 divided by 1.23 is a fourfold change. So that is telling me that this reaction is second order in terms of the nitrogen monoxide. All right, and so these are very typical data sets. You have multiple trials. You have to have a set of trials where one of them is held constant, the other changes, you see what happens to the rate, and then you flip-flop so that you have trials where each reactant is held constant and the other is changed. And you look at how the rate changes. So we can write the overall rate law for this very easily. The rate is equal to the rate constant, the hydrogen concentration raised to the power of 1 times the NO concentration raised to the power of 2. Now I want to point out that this does not match the coefficients from the balanced equation. Remember, they don't have to. They may or may not have any apparent relationship. You can only figure out the rate law and the exponents in the rate law from doing experiments. All right, so now we have the rate law. You'll notice that this reaction is third order overall. All right. And so we can pick any one trial to find the value of the rate constant. All right. So the rate constant is equal to the rate from that one trial over the hydrogen concentration over the NO concentration squared. I'm going to pick trial 3 just because it's easy. It doesn't really matter. So the rate was 4.92 times 10 to the minus third molar per second divided by the hydrogen concentration, which is 0.10 molar, and then the NO concentration, 0.20 molar, but that's squared. And I'm going to get out my handy-dandy calculator here. 4.92. Whoa. Divided by 0.1. All right, and I did that, and I got a value of 1.23, and then I have to work out my units. That's very important, of course. Can't leave naked numbers there. Let me just work this out for a third order reaction. So I have moles per second over moles and molar and molar. All right, so one of those will cancel out. So I guess my units are molar to the minus 2. All right, great. I hope you're finding that these really are not too bad to do. Right? As long as you're familiar with the basics, they should work out pretty smoothly for any problem you encounter. Now, I did want to take a little bit of time and talk about the rate constant more specifically. In general, we know that reaction rates increase as temperature increases. So this is a chemiluminescence reaction from a light stick. Right? And at a higher temperature, you see it glows much more brightly than when it's cooled down. The reason for this, or one thing, there's a couple of things for this. One is that the molecules are moving faster, and so they're colliding more frequently. This also means that the rate constant increases as temperature increases. All right, and you can see in this particular graph, this is quite a dramatic increase with the rate constant. So one thing I want to point out about all these kinetic experiments that we've been talking about you'll find that they report that the temperature at which the experiment was done, they all, when you're comparing experiments, they all need to be done at the same temperature. Otherwise, you're going to not be comparing apples with apples. Because of this temperature dependence of the rate constant. So I just wanted to point that out to you so that you don't get misled by that. All right. Now I did want to point out the units. There are some handy ways for you to figure out what the units should be, and this has been known to show up on AP exams, all right, where, find the rate constant after doing some of this initial rates experimentation or analyzing the data, determine the rate constant, and include appropriate units. I do want to point out that if the reaction is first order, it's going to end up basically with one thing in your unit. It ends up being per second, inverse seconds, right? If your reaction is second order, you're basically going to have two things in your unit. You're going to have per molar and you'll have per seconds. If your reaction ended up being third order overall, as in our previous example, we end up with three things in our units: per molar, per second. Now, we can consolidate the two per molars and put them together, but you can see that there's a pattern here, and that can be really helpful to you when you have to remember what the units are and you're working in a time crunch and you really are feeling pressured. Now, there's another part of this. There's another way of determining the reaction order. All right. Now, I don't really want to spend a lot of time on the integrated rate law right now. They are on the AP equation sheets. I don't want you to worry about their derivation or anything like that, because it's not a math course, it's chemistry. Although we use a lot of math, we're not testing you on your calculus knowledge. All right. But there is something called the integrated rate law. And if you have a first order reaction, it turns out that if you plot the natural log of the concentration of A versus time on the x-axis, you should get a straight line if this is a first order reaction. And the slope of the line, you'll notice it's got a negative slope. The slope is equal to the negative value of k. So if you determine the slope, you can then find the value of the rate constant, which is a great thing. All right. You absolutely need to know this. You need to know that for first order, right, your y-axis is the natural log of the concentration versus time, and that you're going to get a straight line. You have to know this. This is really important. Similarly, if you go to the integrated rate law for a second order process, there's something else we can do that characteristically gives a straight line. In this case, if you plot 1 over the concentration versus time, that's what's shown in this graph here, you will also get a straight line. So if you plot 1 over A versus time, you get a nice straight line, and the slope of that line is equal to the value of k. Again, you absolutely need to know this. You need to be able to know what you can graph that should give you a straight line for first order. You need to know what you should graph that would give you a straight line for a second order. And you need to know the correct label for the y-axis. This is really important. So make sure you know this. We can use this to figure out the reaction order. All right. And so I'd like to do that right now. So we have this reaction. It's a decomposition of nitrogen dioxide. All right. We want to know the reaction order. Well, we can't tell that by looking at the balanced equation. We could do this with initial rates, but we've got another way of doing that. All right. We want to know the order of reaction relative to NO2. Well, as I mentioned before, most things are either first order or second order. It's very rare to see anything that's a higher order reaction overall. Very, very rare. So here's what we're going to do. We are going to take this concentration data, and we're going to take the natural log of that data. And we're going to take 1 over the concentration. We're going to set this up as a table. All right. I don't think we really need to go through the numbers. If you want to crunch numbers, go ahead. But here's what we're going to do. We're going to take this column and plot versus time. And then what we're going to do, and so we'll have a graph. If that comes out linear, we know it'll be first order. If that's not linear, then we'll make this graph, all right, and we'll plot it versus time. So we're going to make two plots. All right. Whichever one of these gets us a linear graph, that's the one that will tell us the order that it is. All right. So if we plot the ln of the concentration data and get a straight line, it's first order. If we plot 1 over the concentration and get a straight line, then we'll know it's second order. Well, I've got the graphs made up already, so rather than take time to actually crunch all these numbers, which just seems incredibly boring, just trust me that you can do it. If you don't believe me, make your own numbers. You can check your own graphs. Do it right on your graphing calculator if you want. All right, well, let's look at the graphs. All right. Well, so here's the natural log versus time. All right. Now you can see it's not a bad relationship, but it's not a really super straight line. All right. You can see some curvature there. All right. So if you go and look at 1 over the concentration, look how beautiful this linear expression is. This is really linear. All right. What this tells us, or what we can conclude from this, is that this reaction is second order with respect to NO2. And of course, NO2 was the only reactant. And so we can say that the rate log for this reaction is this. All right. Sound good? All right. So in some ways, this is really easy. But you have to know the information, or it's not going to work well together for you. But if you pay attention and just keep your mind on what you're doing, I think you'll find that kinetics is really a very approachable topic. It's also a really important topic in AP. So we'll have another podcast following up on reaction mechanisms. Eventually I'll make a podcast on half-life, and we'll try and pull it all together for you. Talk to you next time.